Okay, we're going over this this integral right now. See, Richard Behiel, he made that integral for the Heidelberg integration bee, and so this is my solution to it. I'm not saying that like it's a perfect solution, but I watched the video for a bit and I got some tips, and so then I tried to solve it with what knowledge he provided without actually taking his solution. So oh yeah, also I just made this thing just out of Legos, just to record it. Maybe I'll work on it more, but it works, so that's good. So we have the integral from 0 to infinity, improper integral from 0 to infinity of the sum from m equals 0 to infinity of the sum from p equals 0 to infinity. Let me sharpen my pencil. Of I to the p plus 2n times pi to the p over n factorial m factorial p factorial times x to the n plus m times n plus m to the p dx. Now, an important piece of this integral is that all n are in the set of natural numbers equals 1, 2, 3, and so on. So just counting up from 1. Now this integral looks extremely monstrous, but I found it to be pretty nice personally because well, you'll see. It's not as mean as it looks, okay? We can use some algebraic tricks. So first of all, we need to note down some formulas to use, and this is what I took directly from him because he made this integral. So we have e to the x equals the sum from n equals 0 to infinity of x, or x to the n over n factorial. And so I'm going to put that inside parentheses, and you'll see why in a second. Little comma. And then integral from 0 to infinity of x to the n times e to the negative x dx equals n factorial, which is also gamma of, which one is this? That's just gamma of n, right? Pretty sure. But I'm not going to make any assumptions here. I'm just talking about the gamma function right now. But we do know that for this, this formula, n is also in the set of natural numbers. Okay? So these are the formulae we will use. Yeah, you can see that. Okay. So now, just gotta do some substitution here. Well, not substitution, but we have our e to the x formula right here, and we notice that we have a n plus m to the p and an I to the p and a pi to the p, and so whenever you have multiple things multiplied by each other and they're to the same exponent, you can actually just put them in parentheses. And so that will allow us to take out this infinite sum here, because we have a p factorial on the bottom. So watch this. We have sum from, just m. So the sum from m equals 0 to infinity of I to the 2n, because we took out I to the p, over n factorial m factorial times x to the n plus m. See, we're just leaving that the same. But now we have e to the I pi times n plus m, because we have an I here, we have a pi here, we have an n plus m here, and I'll just let you recall that formula real quick. So that was a really nice substitution there. So now, okay, what do we do? Here, we have an x to the n and an x to the m, so let's expand that out. And there's actually another thing we can do. I'll show you what that is in a second. We still have the n factorial and the m factorial there. I'm going to leave that. But this is also an exponential property. X to the n plus m equals x to the n times x to the m. And then also we have another formula here, e to the I pi equals -1, which actually is really cool. It comes from Euler's formula in complex analysis. And so we can replace e to the I pi with -1, but it's still to the n plus m, all with respect to the x. So we just did a substitution and an algebraic manipulation. Let's also expand out this one here. So m equals 0, infinity. We got I to the 2n, n factorial, m factorial, blah, blah. Okay, I accidentally wrote an m instead. Okay, and then we expand this one out, so we have -1 to the n times -1 to the m dx. And, okay, I'm going to let you look at the Euler's formula again and see if you see something here. Because, yes, we have another application of it. -1 to the m times x to the m is -x to the m, because remember, it's kind of like I don't want to show you, but it's the same case that let us combine the p exponents. And so that simplifies our integral even more, because now we have I to the 2n over n factorial times, what is that, times x to the n, and then times e to the -x, because -1 times x is -x. And we have an m factorial on the bottom and an infinite sum over m over here. Okay. We can also take out these constants of n from the integral, because the integral is with respect to x. So now we have integral 0 to infinity of x to the n times e to the -x dx. And look at that. This is another awesome formula, which comes from the gamma function. The gamma function is an integral defined in real numbers and complex numbers, but that doesn't matter right now. We're using it of n, so that's n factorial, and we have that same thing here. So I will just say I to the 2n over n factorial times, whoopsies. Sorry guys, I left out a -1 to the n factor. I accidentally didn't bring that out. See that one? I forgot about that one. So also out here we have a -1 to the n factor with our constants. Just a little reminder. Okay, -1 to the n, and then since this integral is n factorial, we can say technically we solved it, but let's simplify it and actually get a numerical answer. So this is I to the 2n times -1 to the n. And so the cool thing here is that, look at this. So I squared times -1 to the 1 equals 1. Because here I'll show you a little visual. I could have explained all of these things, but I want to explain this one. Okay, this is 1 equals I to the 4th. And then we have I, and we have -1 equals I squared, and we have I cubed. Okay. So we have I to the 2 times 2, which is 1, and then -1 to the 2, which is 1 times 1, which is 1, and we have I to the 2 times 3, which would be going like, it would be going from I squared to I to the 4th to I to the 6th, so that's -1, and then we have -1 to the 3, which is -1, so that's -1 times -1, which is 1, and so this pattern repeats forever. This pattern repeats forever, and so this tells us that yes, we have the result to our integral, which is 1.